Okay, so today we have Karthik who will talk to us about the scenes behind the scenes of AX equals to B axioms and an open question. Please.
Yeah, thanks for the opportunity to present and welcome everyone to the talk. It's a slightly different topic, perhaps nothing to do with multi-arm bandits, at least as far as I can see. So, in spite of this, I hope this will uh, trigger some interest in all of you towards a very nice approach to geometry and linear algebra. And towards the end, I'll indicate an open question that may be of independent mathematical interest. So this is joint work with my PhD supervisor, Professor Rajesh Sundaresan from IISc Bangalore. So we'll begin with the talk. So I'll be talking about linear inverse problems. These are problems which everyone has seen. So there is a matrix A, there is a vector B, A and B are given to us, and we need to recover a certain vector X which satisfies AX equal to B. So we have a linear system of equations and we need to recover X given the matrix A and given the vector B. Now, such problems are called linear inverse problems and they occur very widely in many applications. For example, if we take the example of image reconstruction, an image can be viewed as being split into pixels, and then an image is nothing but a function defined on these pixels. So there is a function f which we want to learn. Okay, there is an image that we want to reconstruct. So there is an f that we potentially want to learn. And let's say the function f takes the value xj on pixel j. So we don't know what the xj's are. The goal is to learn the x1 through xn, but we have linear measurements with us. And then the goal is to recover the x1 through xn from the set of linear measurements. So this is a classical example of linear inverse problem, and it occurs in image reconstruction, and such problems occur very frequently in, for example, X-ray tomography and CT scans and in all such medical applications. Another example, also very popular, is about learning the frequency of alphabets from a corpus of text. So let's say we have n alphabets, alpha 1, so maybe A1 through AN, and these alphabets occur with some probabilities, x1 through xn, which are not known to us. So in order to learn these probabilities, what we are given access to is a corpus or a body of text which contains strings of these alphabets stringed into words. So there is a huge body of text, and there are some measurements that are made on this text. For example, one could measure for each word in the text whether that word contains the letter E. That's a binary question. The answer to that is either a yes or a no. So that represents one measurement, which I call T1 of Z, for example. Another measurement could be, uh, are the number of letters in that word more than 5? Yes or a no. So that could be another measurement. So that is the T2 of Z. Like that, let's say there are some K measurements that are done. And then we want to find the probability distribution of these alphabets subject to these measurements. In other words, we want to find the probabilities x1 through xn of these alphabets subject to the constraint that they satisfy the measurements on the corpus that we have made. So these are all classical examples. I am very sure you all can think of many more examples. But the question that I am after is there a principled approach to solve such problems? Now, there can be many x's which satisfy ax equal to b, and there may be no principled way to select a given x. One commonly used approach to solve this problem is to first define a certain cost function f, and then we recover x as a minimizer of this function f. So here is the picture. Typically, one defines a function f first. So what you see as a gray patched area is the set of all possible solutions to our measurements. Among all these solutions, we want to find one measurement that can be a good representative element in this class of measurement, in this class of solutions to the measurements. So we want to pick x as a minimizer of f. This is how typically the problem is solved. So for example, let's say we are in a simpler setting when there is just one measurement, okay? So the set L is the set of all solutions that we are after, which satisfy only one measurement, which is A transpose W equal to B, where A is some non-zero vector. Okay, so how does one typically go about solving this problem from an optimization perspective? One forms this function G, one introduces a scalar lambda into the picture, and then the KKT conditions naturally come into play, and they dictate that in case the function f that we have chosen a priori as the cost function is differentiable, then at the point of minimum, that is at the minimizer, grad f should equal lambda times a. In other words, the gradient of f with respect to its coordinates should equal, it should be a scaled version of the vector a which has appeared in the measurements. So there is a very close link between the function f and the measurement itself that we have made. And because we want a solution which satisfies the measurements, this condition naturally comes into play. So notice this structure. We will come back to this structure repeatedly throughout the talk. The important point to notice here is that lambda times a, in other words, a scaling of a is of a very special form. It is of the form gradient of some function. Okay, this gradient of a function is a special kind of a vector. Notice the gradient of f is a n-dimensional vector. Each component is the partial derivative with respect to that coordinate. So it is a very special kind of a vector for reasons which will become apparent later in the talk. So, of course, this can be extended to any set of measurements, any set of k measurements. So, if we have L as the set of all solutions to the system of equations AW equal to B, where A is now a matrix, then the function G will be like this. And then the KKT conditions will necessitate that the gradient of f should be A transpose times lambda, where lambda here now is a k-dimensional vector. Lambda has as many components in it as the number of measurements that are being done. So all of these are there. Of course, we all know some commonly used examples for f. One is the very well-known least squares method. In this method, in order to pick a solution, we choose f of w as the squared L2 norm of the vector. And we pick x as the unique element which satisfies, which minimizes the L2 norm. Another very well-known method is the method of maximum entropy, in which we choose f as the negative entropy, so that minimizing f is same as maximizing entropy. So x is picked as that vector which has non-zero components and satisfies the minimum entropy principle or the maximum entropy principle. So these are some commonly used f. Now, in some instances, what happens is that there is some prior knowledge about the vector that we are searching. The vector that we are searching, remember, is x. But there may be some prior information about that, and that can be represented through a prior guess. So let's say we have a prior guess x star for what this x should be. But now, because we have some additional measurements in the form of AW equal to B, this x star may not satisfy those measurements. So we will need to, let's say, update the x star to something that satisfies the measurements. So in such a case, one popular known method is least squares, but with x star. This is what is called the principle of minimum mean squared error estimation. So here, the f is chosen this way, and x is picked as a minimizer of this particular function. Notice that x star is some prior guess. Similarly, there is a maximum entropy, but there is an equivalent version. The f now is chosen as the KL divergence, and one tries to minimize the KL divergence over all elements in the set of measurements, or all elements which satisfy the measurements. So this is what is called a principle of minimum I divergence or KL divergence. Okay, so so all these are problems of one particular kind. Okay, so there is a certain geometry that is going on here behind the scenes, and that is what I would like to bring your attention to. Notice that we are solving some fundamental optimization problem, but there's a geometric viewpoint to all of this, which is that all of these can be viewed as projections in some way. For example, if we look at the 2 norm, that is the least squares problem, the least squares problem is simply a projection of the vector 0, that is the origin vector, to the set of measurements that we are interested in. So you can think of the 2 norm minimization as a problem where the a priori guess about the vector is the origin vector, but the origin vector may not satisfy the measurements. So we need to update the origin vector to satisfy the measurements. And that can be viewed as projecting the origin onto the set of all measurements. Similarly, if we look at the minimum mean squared error estimate, it is about projecting a prior guess X star to the set of all measurements L. Similarly, if we take the maximum entropy principle, that can be viewed as projecting the uniform distribution onto the set of measurements. When you don't have any information about the probabilities of the letters in the corpus, the best you can do is to assume that they are uniform. Why would some letter or some alphabet be more likely than any other in the absence of measurements? So a priori guess would be uniform, but that may not be true. You want your probabilities to satisfy the measurements, so you update the uniform distribution to something which satisfies the measurement. So that's a projection of the uniform onto the set of measurements. Finally, I divergence, as I said, is simply the projection of X star onto the set where the geometry is now arising from KL divergences. You should think of KL divergence as the new metric when you're doing this divergence. No, sorry, when you're doing this geometry, when you're doing projections here. So all of these are examples of projections. In other words, what I want to say is the very commonly known approach of first defining a function and then recovering X as a solution to the minimum of this function simply defines a projection rule. And by projection rule, mathematically, what I mean is, given a set of measurements L, given solutions to the measurements that is represented by L, and given a prior guess X star, the projection rule is simply going to give me an element of this set L which satisfies the measurements. So pi of L given X star is the projection of X star onto the set L. Of course, it should be an element of L, right? We are looking for something in the set L. So that is where it is. Now, let's say we have a function f. So this function f earlier, I had just written it as f of w, but if you have a prior guess, you can treat the prior guess itself as a variable, and then you can define a function of two variables now, f not only of w, but also of x star, which depends on the prior guess x star. And then there is a projection rule. Let's try to connect these two. We have seen that connection till now. Let me give that a formal name now. Let's say that pi is generated by the function f if the projection of x star onto L is simply the minimizer of this function f over L. So this is what we have commonly seen until now. This is how we have been recovering the unknown vector x. The unknown vector here is pi of L given x star. Okay, very nice. So we have all of this. Now, one natural question that anyone can ask at this point is every projection rule generated by a function like this? That is, if we want to recover vectors to solutions of linear systems of equations, is function minimization the only way? Is every projection rule always defined by a function? That's the question. So these are the examples from before. So this is the question we are after. Is every projection rule always generated by some function? And answers to this question were provided by this giant in information theory, Imre Cizar, in 1991 in this seminal paper which appeared in the Annals of Statistics, where he also gives a slightly different approach, not the function minimization approach, but a slightly different approach. And he says the function minimization approach and this other approach that he tells in the paper are very closely related to one another. So what he says is, we will attack the projection rule directly. Okay, we know that there is a projection rule, pi of L given x star. Given a L, given a x star, it tells me what is pi of L given x star. So it's a mapping from L comma x star to something inside L. Now, if this projection rule, that is just this mapping, if this mapping satisfies some nice properties, then we can say that it is actually generated by a nice function. Okay, so in his paper, he goes on to say that, look, there are some axioms or some rules that I want the projection rules to satisfy. If these rules are satisfied, then these projection rules ought to be generated by some nice functions. For example, Suppose the projection rules satisfy regularity and locality. These are some axioms. Don't worry about the definitions. But suppose they satisfy regularity and locality conditions, the mapping that is, given a L X star, I give you something in L. Just this mapping, if it satisfies the properties of regularity and locality, Chizar shows that that projection rule which satisfies regularity and locality ought to be generated by a function f which has this particular form as you see on the slide. It should be sum of component functions, each of the component functions being continuously differentiable and strictly convex. Has to be this function. It has to be a function of this form. And it's vice versa. Suppose you have a function f which is a sum of component-wise functions, each of which are continuously differentiable and strictly convex. If you minimize this function over any L, and if you look at that kind of a mapping, which you get by minimizing this kind of an f over sets of linear measurements, that projection rule which comes as a result of minimizing f has to be regular and local. It's a vice versa result. Similarly, if you throw in another property which is that of subspace transitivity, then f necessarily has to be a Bregman's divergence. Bregman's divergence, for those of you who are not aware of this, is a large class of divergences, among which KL divergence and the two norm Euclidean distance are very well-known examples of Bregman's divergence. Okay, so it's a very large class of divergences. So regularity plus locality plus subspace transitivity for the projection rule implies that projection rule has to be generated by a Bregman's divergence. Conversely, if you minimize Bregman's divergences, the projection rule arising out of such a minimization exercise has to satisfy the properties of regularity, locality, and subspace transitivity. Likewise, he says, if you throw in two more conditions, which is maybe statistical and scale invariance and location invariance, then the projection rule has to be generated by the mean squared error function. So that is the minimum mean squared error estimation process, whatever we have, that is actually a projection rule which satisfies a lot of conditions. Whether you want these conditions or not, these conditions are there in the background. So the point of the point of this work is that whenever we want to choose some natural candidate functions for minimization and picking good solutions to the set of linear systems of equations, we should be very careful what these functions, what these projection rules are bringing with them. In the background, they are having a lot of set theoretic properties such as regularity, locality, subspace transitivity, etc. I will tell you a few of these just to give you a flavor of what these rules look like. For example, what is regularity? What is subspace transitivity? And you will see that if you don't want such rules, you better not be minimizing the KL divergence, or you better not be minimizing the least squared or the squared error. You better not be minimizing any Bregman's divergence. So it's very important. The choice of function has to be very carefully thought about in terms of what goes on behind the scenes. And I think this work, which was brought out by Chizar, is one seminal work in this field, which has enabled this kind of a thought process in the community. Now, having said this, I am sure many information theorists out here may wonder where does another brother of KL divergence, which is the Rayleigh divergence, sit in this class. So Rayleigh divergence is a valid divergence, and it has been extremely well studied in the literature, in the information theory literature. And Rayleigh divergence projections have shown to have very similar properties as KL divergence projections, and they're in fact a parametric generalization of KL divergence projections. So where does Rayleigh divergence sit here? In other words, if we were to consider Rayleigh divergence in some application, and if we were to minimize the Rayleigh divergence, where would the resulting projection rule sit? What properties would that satisfy? Now, in trying to answer this question, towards the beginning of my PhD, I started looking at a work from one of my ex-lab mates at that point of time. He had done a work on a certain family, a certain parametric family of divergences, which is not the Rayleigh, but it is closely related to the Rayleigh divergence. As of today, as far as I know, it is what is called Sundaresan divergence. It's also called relative alpha entropy. So I have linked some papers here. Please go through it if you want to see the exact definition of what relative alpha entropy means. Essentially, relative alpha entropy, although it has entropy in it, it is actually a divergence. And it is a divergence which is very similar to Renyi divergence, but not exactly the Renyi divergence. But whatever it is, Kumar and Sundaresan, they discovered a family of projection rules, those arising from minimizing relative alpha entropy. These projection rules were known to satisfy regularity, subspace transitivity, but not locality. Recall from the previous slide, if all the three are satisfied, regularity, locality, and subspace transitivity, the projection rule has to be a Bregman's divergence. But locality is not satisfied here. Also, relative alpha entropy is not a Bregman's divergence. Renyi divergence is also not a Bregman's divergence. So the question that arises is this relative alpha entropy, here alpha is a parameter, so it's a family of functions, family of divergences, one for each alpha. So are these relative alpha entropy projection rules the only projection rules which satisfy these three properties: regularity, subspace transitivity, but not locality? We were after this question, and we realized that this question has a lot more meaning in terms of trying to understand what kind of properties are satisfied when we look at minimizing the relative alpha entropy or minimizing Renyi divergence. Notice that minimizing Renyi divergence or minimizing relative alpha entropy, as it has been indicated in the papers I have shown at the bottom of this slide, they occur very naturally in statistical physics. So in statistical physics, people have considered minimizing relative alpha entropy, minimizing Renyi divergence. So we wanted to understand in those statistical physics context, what exactly is going on behind the scenes. When they minimize the relative alpha entropy, in terms of projection, what exactly is happening behind the scenes? At a set theoretic level, is regularity satisfied? Is locality satisfied? Is subspace transitivity satisfied? We were after that. Thankfully, Kumar and Sundaresan answered this particular thing. But because it doesn't satisfy locality, this opens up a new possibility for a family of rules which are only regular and subspace transitive. Are these the only ones, was the question we were after. So that's the main question that we attacked. And our quest was to come up with answers similar to what Chisar has given in his paper. So Chisar has said, if regularity and locality are satisfied, the projection rule ought to be generated by an f which can be decomposed as a sum of functions, individual components, all of them being continuously differentiable and convex, strictly convex. And Chisar also showed regularity plus locality plus subspace transitivity if and only if it comes from a Bregman's divergence. Can we say something on the similar lines by removing locality? What does regularity plus subspace transitivity entail? In particular, what does regularity entail? So these are the questions that we were after. So I would just like to give a flavor for what a study of such questions looks like, where does it lead us to, and towards that, I will eventually want to come to an open question that I want to present. This open question is something that is that comes from geometry. Okay, but I want to link all of this and I want to present that open question to you and possibly gather your thoughts on this and trigger interest in this direction of thoughts that the community has been trying to pursue. So maybe this can be a good point to stop and ask the audience if there are any questions before proceeding. So I can take maybe one or two questions at this juncture. So if anybody has questions, please let me know.
Will these terms be defined soon? The regularity and transitivity?
Sorry?
Regularity and subspace transitivity, will they be defined shortly?
Yes, I'm going to define them.
Okay, thanks.
Yeah. Okay, so we know, so as Professor Jonathan Scarlett asked me, it's important to know what these mean, and I don't want to define everything. I'll just give a glimpse into what regularity means and what subspace transitivity means. So for the other axioms such as locality and scale invariance, location invariance, etc., I would urge you to look at Chisar's paper. So let's come to regularity now. So let's keep the goal in mind. we want to ask ourselves, what does regularity mean? If a projection rule satisfies regularity, can we say it is generated by a certain function? If so, what is the structure of that function, etc.? That's where we are after now. So we are given a projection rule. Regularity axiom itself has 3 sub-axioms in it. Don't worry about the definitions here. I'm going to explain through pictures. Okay. First, a projection rule is said to be regular if it satisfies 3 properties: consistency, distinctness, continuity. First, what is consistency? Consistency means, suppose you have a set L of measurements. Suppose the projection of X star onto L is some X, but that X lies inside a subset L prime. All these are known. Now, if you strip away everything other than L prime and if you retain only L prime, if you give this L prime to the projection rule, the projection rule should not pick a different vector as its projection. In other words, the projection of X star onto L prime and the projection of X star onto L are the same in spite of the additional measurements that are there in the set L. So additional observations don't give any reason for us to change our selection. So this is like saying there are 3 parties participating in an election: party A, party B, party C. When party C is participating in the election, because I hate party C, I am going to vote for party A. But now, if I tell you that party C is not participating in the election, you should still not change your vote for party A. If you happen to change it for party B, that means you are not satisfying consistency. So additional measurements should not give you a reason to change your original selection. That is consistency. Distinctness, as the word itself says, if you take 2 different sets of measurements, L and L tilde, okay, so the axiom of distinctness is stated for those L and L tilde which are solutions to just one set of measurements. So M here is the set of, it's the class of all those sets which are generated by just one measurement. So if you take L and L tilde, which are 2 distinct sets, then the projections on these 2 sets are also different. That's what distinctness axiom says. And then continuity, as you know, it's simply continuity in the actual way continuity is defined. But here there are vectors, and you impose the topology on these vectors arising from the usual Euclidean topology. So if you restrict yourself to the class of all sets of a given dimension, what do I mean by dimension? For example, if there is a set L which is of the form set of all W which satisfy A transpose W equal to B. In other words, L is the set of all solutions to one measurement. Because there is one measurement, it has dimension n-1. There are n-1 degrees of freedom. If there are 2 linearly independent measurements, that is, L is the set of all W which satisfy 2 sets of linear measurements. A1 transpose W equal to B1, A2 transpose W equal to B2, where A1 and A2 are linearly independent. In that case, there are 2 degrees of freedom which are already fixed, and therefore that set is of dimension n-2. So like that, you collect all sets of dimension n-1, all sets of dimension n-2, all sets of dimension n-3, etc. up to like you collect all sets of lower dimensions. If you restrict your projection rule, which is now a mapping, by the way, if you restrict this projection rule to any given collection of the sets of a particular dimension, in that collection it is continuous. Continuity defined in the usual way. There are matrices which are converging to some other matrix. It's the usual Euclidean topology that is imposed on each row of the matrix. So pi restricted to sets of a fixed dimension is continuous. So pi of dot given x star, which is a projection rule, remember, if you fix the x star, it is going to eat L and it is going to spit out a member of L. So it's going to eat L as L varies continuously, as L varies in a smooth way. The projections also vary in a smooth way. That's the idea of continuity. And what is subspace transitivity? If you have 2 sets, L prime and L, such that L prime is a subset of L, If you want to project onto the smaller set, you can project it in two iterative steps. First, you can project to the bigger set L. You can project that projection onto the smaller set L. So this is what is the it's what is called a axiom of subspace transitivity. And if you recall, regularity plus subspace transitivity plus something else called locality, which I have not defined here, means that the projection rule has to be generated by a Bregman's divergence. And if there are information theorists here, they will very easily recall that any Bregman's divergence satisfies a certain Pythagorean property. The distance between projection to a smaller set can be viewed as the sum of the distances between projections to a bigger set and that projection to the smaller set. So this kind of a subspace transitivity rule is built into the projection rule, which is generated by a Bregman's divergence. So Bregman's divergences are of course very nice, but as I said, Renyi divergence doesn't satisfy locality. Renyi divergence is not a Bregman's divergence. In spite of that, it has subspace transitivity, and in spite of that, it also has Pythagorean property. There is something that is going on behind the scenes here that we are trying to understand. So I defined regularity. Regularity has three properties: consistency, distinctness, continuity. And then there is subspace transitivity. So where are we trying to get with all of this? So I'll not focus on subspace transitivity because our approach back during my PhD days was to try to understand, first let's try to understand regularity because it is common in both. Whether we want to study regularity plus subspace transitivity or we want to study only regularity, finally we have to come to regularity and we have to try to understand what that means. So I will now tell you a very nice implication of regularity. So just be with me for a couple of slides. So regularity has this very, very nice implication, and this implication is already shown in Chisar's paper. This is not something that we have come up with. So if you, so here L0 of X star, whatever I write here as L0 of X star, this is the set of all those L. L, by the way, is the collection of all solutions to our measurements. So L0 of X star is the collection of all those L for which the projection is X star itself. X star is our prior guess. It's the collection of all those sets for which the projection is X star itself. So if you restrict your attention to the class of all n-1 dimensional sets, recall n-1 dimensional means it has only one constraint. So I'm looking only at Rn for now. If we consider probability vectors, there is one more constraint and therefore it will be dimension n-2 in that space. But for now, let's restrict ourselves to Rn. We will not go out of Rn. So in Rn, you look at all those sets which have only one measurement in them, okay, which are defined by one measurement. Okay, so if you restrict yourself to the class of all those sets which are defined by one measurement, but you exclude out those sets for which the projection is X star itself, then that collection of sets has a one-to-one onto and continuous mapping with the set of all Rn punched at X star. In other words, you exclude X star from Rn. This set of all n-1 dimensional sets has a one-to-one onto relationship with Rn minus X star, everything other than X star. So a homeomorphism, the technical term homeomorphism that I'm using here, simply means that it is one-to-one onto, that is, it is bijective and continuous. Bijection plus continuous is homeomorphism. So one very nice implication about this homeomorphism result is that if you take any vector W, which is not X star, there is a unique L, which is a n-1 dimensional set now. There is a unique L. Of course, the projection onto L is not X star. Okay, the projection of X star onto L is something else. But there is a unique L in this family of n-1 dimensional sets whose projection is W. If you take a W, there is a unique L such that the projection of X star onto L is W. So here is the picture. Given any W, any vector W which is not X star, there is a unique L which I define like this. There is a unique L such that the projection of X star onto L is W. That is what it means. Of course, if it is a n-1 dimensional set L, that n-1 dimensional set will be defined by a normal vector, because any n-1 dimensional set has to be of this form. It has to be having one measurement. So therefore, it can be defined by a vector A and some scalar B. Now that scalar B, because W is there inside this set, that B can be written as A transpose W. Essentially, this L vector is defined by a unique normal vector, which I call as A tilde of W given X star. So let's try to come out and let's see what's the big picture. X star is, let's say it's fixed for now. Don't worry about the X star. That's the prior guess. Regularity implies, so you look at the projection rule arising from X star. That is, you always want to project X star. You are not changing the prior guess. I want to project X star onto n-1 dimensional sets. That is, all those sets which satisfy only one measurement. So now, regularity implies one very important condition, which is that the projection, if you take any vector W which is not X star, there is exactly one n-1 dimensional set such that this W is the foot of the projection. It is the foot of the projection from X star. There is exactly one such L. Of course, that L has to be defined by a normal vector, A. So you look at the A. You are given a W, look at the A for the W. You are given a W, look at the A for the W. This is going to define a mapping from W to A of W, or A tilde of W, as I call it here. There is a mapping. Now this homeomorphism very importantly implies that this mapping is continuous. This is a vector to vector mapping, and continuity is simply continuity in the topology of Rn. Okay, so this is a vector to vector mapping. This in geometry terms is called a vector field. I'm sure many of you have heard of the term vector field in electromagnetics, where you study electric fields and magnetic fields, and you hear the word field, vector field everywhere there. So this mapping from W to A tilde of W is a continuous mapping, and of course it is continuous only for W not equal to X star, because that's what we said. And we can define a continuous extension of the A tilde by defining A tilde of X star equal to 0, the 0 vector. So with this, we have a vector field, very nice vector field. Okay, so regularity, just regularity, gives us a very nice vector field. So where am I heading? Why this vector field? Why is all of this coming? What do I want to do with this vector field? Recall this slide I showed you earlier. We said whenever we are minimizing a function f, if the f is differentiable, f has to satisfy a property like this. The gradient of f has to be related to the A. Notice that the L I have taken here is a n-1 dimensional set. It has only one measurement, A transpose W equal to B. So the A has to be related to the F in this particular way. The gradient of F has to be a scaled multiple of A at the point of minimizer. So the question is, we have a vector field here. Now, in order for us to go from this vector field, and if we want to ask ourselves, is the regular projection rule generated by a function f? If that's the question that we are after, that regular projection rule led us to continue that some vector field. But ultimately, the condition that the vector field has to satisfy is, can we scale this vector field? This vector field a priori may not be of the form gradient of some f. If A tilde itself is of the form gradient of f, we are done. We know that A tilde itself is gradient of some function, and we can readily conclude that the regular projection rule is generated by that function. But if the A tilde is not of that form, at least can we think of a scaling of A tilde that will make it look like a gradient of f for some f. We don't know what the f is. Okay, so if we just trace back where we were given a regular projection rule. From that, we extracted a continuous vector field. We are now asking ourselves, can this vector field be scaled so that the scaled vector field is of a special form? What is the form? It is a gradient of some function. Not every vector field is a gradient of some function. Only some special vector fields are of the form gradient of some function. So can the A be scaled so that it looks like the gradient of some function? If the answer to this question is yes, we can readily conclude that the projection rule pi, which is regular, has to be generated by a differentiable f. There is no extra structure for that f as of now. If the answer to this question is yes, if the answer to this question is yes, all we can say is that the regular projection rule has to be generated by some differentiable function f. There exists some function which generates it. Unfortunately, this is the question that remains open. We don't know answers to this question. That is, if we are given some arbitrary vector field A, can we scale it so that the scaled vector field has a special structure? It is the gradient of some function. A vector field which has this particular structure is called a conservative vector field. In the literature, it is called conservative vector field. For example, if you remember, electric field is a conservative vector field because it can be represented as a gradient of a potential, negative gradient of a potential in some nice cases. So the conservative word comes from there. So given some continuous vector field, which a priori may not be conservative, can we scale it so that the scaled vector field is continuous? Oh, sorry, the scaled vector field is conservative. It's a very open, and it's possibly a very generic question to ask because there is no additional structure that we have except for continuity. Regularity only implies continuity of A. But given any A which is continuous, is this possible? Can we find a scaling which will make it conservative? This is something which mathematicians also have been struggling, and they have not yet found a solution to this. So during my PhD, I approached a lot of people in the math department at IISc, and most of them said this is still open. It's a very hard problem to attack. Of course, we know the answers to this question in some cases. For example, if A is like this, if A of W, which is a vector field, is W divided by norm W, and the lambda of W is norm W, naturally A times lambda is simply the vector W. And all of you know that this vector W can be written as the gradient of F, where F is this function. So which, in other words, what I'm saying is, if you trace back, notice that F is the least squares function. So the projection rule that's generated by this least squares function guarantees that A is of this form. And because A is of this form, it is generated by F. And we know that regular projection rule, in fact, the least squares projection rule is not just regular, it is much more than regular. Because it is regular, naturally it satisfies this condition. So we anticipate that with the help of mere regularity, we should be able to answer this question. That is this question in general, but we also have a counterexample. The counterexample is, if we are in R3 with XYZ as the coordinates, suppose A of XYZ, which is now a vector, is Y01. Okay, if we take this vector, one can show that there is absolutely no lambda such that A times lambda is of the gradient form. Because if at all there were a lambda which is of the such that lambda times A is of a gradient form, then some necessary condition is going to get violated. Okay, I have not written that necessary condition here, but one can show that. So there is a lot of discussion that's happening even on Math Stack Exchange about this problem, and there are not very concrete answers about this. In fact, I got this counterexample from Stack Exchange. I had raised a question, and one good mathematician had answered. He gave this counterexample actually.
So here, right? Can I ask a question? Here in this your counterexample, the F is still the half squared norm. Is that so? The capital F?
No. So in this second example, we don't know because there is no
generic thing that you minimize. Capital F.
So we are not coming from the point of F. We are only coming from the point of projection rule. So I mean, let me just complete one more statement that I had to say. So we of course have this counterexample, but does this vector field A actually arise from a regular projection rule is itself the question for which we don't have answer. So just to answer Vincent's question, we are not starting with an F and asking what kind of a projection rule it satisfies. Rather, we are starting with a projection rule, possibly regular, we want to understand what regularity means in a projection rule. We know that regularity means there is a vector field which is continuous. I am trying to play with that continuous vector field. I am taking examples for the continuous vector field and trying to understand whether the continuous vector field can be transformed into a gradient form, into a conservative form. So that conservative vector, that vector field, continuous vector field, we cannot choose some arbitrary vector field, because that vector field which we choose arbitrarily may not be arising from a regular projection rule. So we have to be very careful when we choose the A. But certainly there is this counter example. We don't know whether this kind of a can come from a regular projection rule, because regular projection rule implies a continuous A. That much we know. This A is continuous, very good. But does this continuous A, and for this continuous A, there is no scaling, which makes it conservative. So the question that remains is, can such A also come from regular projection rules? If so, mere regularity is not enough. We need to impose additional structure on the projection rule so that this kind of A, these kind of bad A don't arise. So really we cannot say just from this whether the function that we are after is the half times the norm square. Merely from that we cannot say. So even if that function is there, gradient of that cannot be equal to this, because we have shown there is no lambda such that lambda times A is the gradient of f for any f. So there is no such lambda, there is no such scaling that is available. So this is the open question that I wanted to indicate to all of you. This kind of an open question comes in many places in statistical physics, in trying to understand what kind of divergence measures should we naturally use in those applications. So there is, like, statistical physics is there. Then there is of course this whole theory of there is this whole literature surrounding projections in KL divergence, where Chisar has contributed a lot. There is a whole theory of projections in Renyi divergence. There is a whole theory of projections in L2 norm. And then there is compressed sensing, where there is projections with respect to L1 norm, although like L1 norm and even L0 norm, although L0 is not really a norm, but L0 minimization has been studied very widely in the literature on compressed sensing. So is it, the question that all of this is trying to indicate is, in a setting like compressed sensing, is L0 the most natural thing that one should be thinking of? Of course, people like Terence Tao and Donoho have given many answers from different perspectives to that. But from a set theoretic perspective, from a very, very fundamental perspective of what's going on behind the scenes of L0, or what's going on behind the scenes of L1 minimization, are those the most natural things to consider? For example, what if L0 is also satisfying subspace transitivity, but we don't want subspace transitivity in some application, in compressed sensing itself? For example, what if L0 is satisfying regularity, but we don't want regularity in some application? So in an application where we don't want regularity, for example, consistency is something which is natural, but what about distinctness? We may not want that kind of a distinctness, or we may want distinctness. So it really comes down to thinking about what natural properties we want in the problem, then going back and defining an appropriate function which makes sure that all these properties are there. So it is for this kind of a reasoning and this kind of a thought process, I feel Chisar's work is extremely helpful. And I know of very few works which have like dealt with Chisar's work in detail. So I am still very much open to looking at this problem in slightly more detail. At the moment, we tried to attack regularity. All that we could end up with is some continuous vector field for which there is no answer to whether the continuous vector field can be turned into a conservative continuous vector field. And that's where we actually stopped. And I took a different direction during my PhD because of paucity of time. But I'm really interested in problems like this. And if any of you are also interested and we can collaborate, I'll be very happy. So with that, I'll conclude my talk. Essentially, in this talk, I spoke about two approaches to solving systems of linear equations. One is a natural function minimization approach that we are all aware of. And then the second is an axiomatic approach. And both of these are very closely related to each other. And personally, I feel the axiomatic approach should be studied in slightly more detail so that when we know what axioms or what properties our problem setup ought to have, we can then try to extract a function naturally through this complementary axiomatic function minimization approach of Chizar's. We can try to extract a function which meets all the axioms we want. And in the talk, I described the axiom of regularity in some detail, and I showed what connection it has with conservative vector fields. And the final open question that still remains, this is a general mathematical open question. It has nothing to do with information theory as such. We can pose it to mathematicians and ask their suggestions as well. If we are given a continuous vector field, which is not necessarily conservative, is there a scaling of this continuous vector field that can make the product conservative? So if we can answer this, we have some hope about regularity. We can get some insights into regularity. So this is where I would like to conclude. Thanks for your attention, and I'll be happy to take questions.
Great, thank you very much. Does anyone have any questions?
Yeah, so I understand that this may be new material to many of you, but I hope this has triggered some interest in this, in the line of work that Professor Rajesh and I were trying to pursue. I don't know of many people who are doing this, doing work something like this, and we are really, to be very frank, like this is a confession, I would say. We are really out of ideas. We don't know how to proceed from here. Of course, it may be worth looking at subspace transitivity also in some detail, trying to consider subspace transitivity and seeing what that entails. But we haven't explored it yet, and hopefully we can get some answers to this question.
Yeah, I think someone would know how to would be able to provide some input on this because Marco has also looked at information measures from axiomatic perspectives, and he's also very interested in projection rules. So perhaps you can talk to him at some point. Yeah, and he knows about all these different all these different divergences and so on.
So who did you say has looked at this? Who is the person?
Marco Mitchell, my collaborator.
Oh, okay,
He's
okay.
around, yeah.
Yeah, in fact, I think there are many other people among the people who Chizar has cited in his work are Axel and Daroxy and I think Schillings, and there are many people who have tried to attack from an axiomatic perspective. I think Chizar's work opened up a lot of possibilities because there is also some indication of some connection to the compressed sensing framework in one of his axioms, actually. So I did not describe that axiom here, but I think his paper has something that we can take away and possibly investigate that in slightly more detail.
Okay.
But yeah, I mean, that's the best I can think of now.
Okay. Yeah. Thanks a lot.
Yeah, and this paper is available freely online. Yes, we can get it from Google Scholar. We just type the title of the paper. So I'll just go to that slide for those who are interested. Yeah. So it's called Why Least Squares and Maximum Entropy, an axiomatic approach to inference for linear inverse problems.
Okay.
So one can Google this name and we can get this copy.
Okay. Yeah.
I'm just seeing the chat to see if there are any more questions.
There are many questions in the chat, actually.
Okay.
There were many questions in the chat. I think.
Okay. Hopefully, I have answered some of them.
Shi Xiong, he also is very interested in maximum entropy and he has some results, but I do not know what are his precise results. He just told me that he's interested in maximum entropy, which is something mentioned. Yeah. Yeah. Does this so the question does not actually involve the properties of F. The question is a question concerning the fact that A is continuous, A is a vector field, and whether it is a scaled version of F, of some F.
Yeah, so Correct.
Right? But what is
Yeah.
the family of Fs that we are concerned about here? Maybe I missed
Yeah.
that.
So I think if we have to, if we want to come to something like gradient of f, naturally f has to be differentiable.
Yes,
Uh,
yes, yes.
but
But are there any other
maybe
conditions?
possibly quasi-convex. I think that that's the like the most general family that I can think of. Maybe some extra conditions need to be imposed on. So the thing is, f is a final output that we are after. Perhaps some more conditions on the a tilde itself need to be imposed. So currently, my question revolves around playing with a tilde that's coming here, and the a tilde is coming from a regular pi. So if it's coming from a regular pi, we have still not understood if a tilde has to satisfy some natural constraints, or it has to satisfy some structure. For example, can the a tilde be the a tilde from the counterexample I showed?
Okay, okay.
So can such an a tilde arise from a regular pi? That is also, it's not clear. We don't have an answer for that yet. So we are proceeding in one direction. The other direction still needs to be explored in some depth.
Okay, great. Thank you. Thank you very much. And thank you
Yeah.
very much, everyone, for coming. I'll see you next week.
Yeah,
All right.
thanks.
See you. Bye-bye.